Yeah, thanks, Ivan, and thanks for the invitation. It's always a pleasure to come to Dortmund. Long and old ties, so we had a lot in common with Ludwig Danzer, as you can imagine. I mean, you all know the story about the Penrose tiling out there, and later with Rudolf Scharlau. And then I've been here on a number of occasions, invited by Friedrich. And today I want to tell you a little bit about this maybe somewhat spectacular discovery of a monotile in the Euclidean plane called the hat. So I'm sure some of you have seen that. It made it to the front page of the New York Times. And there's a lot of hype about it, but not all claims about the tiling that you read in all these things like Quanta magazine or so are actually right. So I'll point out a few. So here's my plan for today. I will talk a little bit about this hat and also maybe say a few words why we should care. And my point will be this is not just a curiosity. It really means something, and we haven't fully understood what it stands for, yeah? But we have understood some things. And to analyze it, we will need to go through a number of steps coming from topology, harmonic analysis, and dynamical systems. And this is joint work with a number of colleagues I had on the first transparency, in particular Franz Gähler and Lorenzo Sadun. And none of us could have done it alone. So this is a relatively good example of a challenge that really needed to bring different disciplines together to solve it. So that will be this. And then we will learn a bit about the cap tiling. So cap is obviously also some kind of a hat, but it stands for more than that, as we shall see. And then we will kind of see how long-range order can be shown and even quantified. And I explained in the pre-colloquium a few ideas that will show up here again. And if time permits, I will actually also tell you a little bit about the other monotile that was discovered soon after, a name called the Spectre. All right. So here is a patch of the hat tiling. And whether you view it as a hat or as a shirt is a matter of taste. But you will see white and black versions in this image, and the gray versions. And the gray versions are reflected versions of the white ones. So this is already one reason why this is not a real monotile, even though the authors claim this very strongly. But O2 is not connected. And I mean, rotated copies are fine, but reflected copy, some people find it okay, and other people say, no, this is not yet the final solution. Yeah? The other thing that's strange is that you can see there are many more white objects than gray objects. Yeah? And in fact, you can quantify this. The frequency ratio of white to gray is the fourth power of the golden ratio. And that means if you reflect the entire thing and then exchange white and gray, you get another solution with the same tiles, but that's different. So in that sense, you have actually two tiling classes that are reflections of one another. Yeah? Crystallographers call this an enantiomorphic pair. And that's another step where, so to say, the purists say this is not yet the solution, the ultimate solution of a monotile problem, because the ground state, whatever that means, is not unique. We'll come to that later. Okay. So there are predecessors that in the discussion about the hat are normally wiped away. So of course you all know the Penrose tiling because it's out there. That's something where two tiles force aperiodicity. Yeah? So if you start with these two objects, and we put them together so that the arrows match. There are tilings of the plane, but only aperiodic ones, aperiodic in the strong sense. And Penrose derived it by analyzing an old image of Kepler in one of his books. He has, so to say, a table of crystallographic configurations. There's one with decagons. And it's clear from the text that Kepler knew this is not something that you can do continue periodically, that you need something else. But the patch is so big that Penrose actually did find an overlay in another version of the Penrose tiling explaining and extending this. And he explained this himself in Tübingen in the so-called Kepler lecture. So in a certain sense, Kepler's drawing is a predecessor of the Penrose tiling. Another interesting story is that if you go from the tiling problem to the covering problem, there is a mono-cover known due to Petra Gummelt, former student of Christoph Band in Greifswald. And that is something that works as follows. So you have this object with these funny decorations, and you can put it next to each other, and you can also put it overlappingly next to each other, but in a very specific rule so that certain patterns are avoided. And if you do that, you can cover the plane, but only aperiodically, and this time it's just this one thing. And because it's mirror symmetric, it's really just one. And every covering of the plane by this Gummelt decagon, as it is called, is equivalent to one Penrose tiling. So if you re-describe Penrose tilings by a cover of the plane with allowed but finitely many overlaps, then this would be it. Yeah? Penrose himself wasn't quite satisfied with this and was looking for a monotile version, and he almost got it. And he calls this the 1 plus epsilon square tiling, because this is something that mediates the information across an edge, and this one mediates the information around a corner, and that's epsilon and epsilon square. But I mean, you can turn it around as you want. It's a tiling with three prototiles, so it's not a monotile. But then there's Joanne Taylor of Tasmania, an amateur mathematician. She knew that if there is a monotile, you should indeed, like Penrose did, start from a hexagon and find local rules to do it. And she found it, and this is her solution. It's a hexagon with a certain decoration, and then you have rules for neighboring hexagons, so the lines have to go through, and a rule for next to nearest neighbor hexagons. So the points of the next to nearest neighbors must satisfy this little thing. And then this is a monotile with a unique ground state. However, again, you also need the reflected version. So it falls short of the strictest possible version of it. And she published it together with Taylor-Socolar. Yeah? And in the discussion about the hat, you always find that this does not qualify because of the next to nearest neighbor interaction. There's no geometric realization of this without markings, and that's not true. There is a version of this which works by just geometric rules alone, and this version is connected, but it's not simply connected, so it has some pinch points. Yeah? So that's so to say a shortcoming of the Taylor version. Yeah? But there are lots of predecessors, and Marjorie Seneschal said on HatFest 2.5 years ago that the hat had never been discovered by mathematicians because they would not look for it. It could only have been discovered by amateurs. And then one person of the audience said, but what about the Gummelt cluster? That's something completely different. No, it's not, because this was set as a PhD thesis by Christoph Band to Petra Gummelt, find a covering version of the Penrose tiling. So that was a very clear-cut thing. So many people have looked for this, but so far not successful until Hat and Spectre, which were discovered by not really an amateur, but a retired lithographer who was interested in polygons with high Hage numbers. So that's what his original motivation was. And then he found this hat and couldn't see that it has a finite Hage number. And then the computer science colleague Kaplan and Myers, they ran their programs and found that the Hage number has to be at least 20, but the record holder for Heesch number, I think, is 6 or 7. Heesch number is the number of complete shells with the same tile you can build around a starting block. Yeah? Then it was suspected that the Heesch number might be infinite, saying that this is a tiling, and then they proved that it's actually non-periodic. Okay, why should we care? Well, there's a lot of fun in it, for sure. You can also make cookies, like I had on my very first transparency. You can download the file for your 3D printer from the internet and then make Christmas cookies out of that, yeah? And you can do it. It's a lot of fun. And it is a bit special in the sense that it is the first purely geometric monotile that is simply connected. Yeah? So that's definitely progress. Yeah? But it is interesting because if you recall what we know about sphere packings, then you very quickly come to the point that denser sphere packings need not be lattice-like. So we know, due to Wiasowska, that in 8 and 24 dimensions that is the case. Yeah? The denser sphere packings are related to the E8 root lattice and the lambda 24, the Leech lattice. But in other dimensions, it's not so. In 2 dimensions, it's clear, it's the hexagonal packing. In 3 dimensions, it's Kepler's conjecture, now proved by Thomas Hales. But already there is the lattice version, but it's built from stacking layers. And you can have different stacking sequences. So there's an uncountable number of non-lattice-like packings of the same density. So you already see, if dimension grows, it might be trickier. And starting in higher dimensions, I always forget whether it's 5 or 6, there are sphere packings that are denser than every lattice packing. Yeah? As far as I remember, it's not known what the densest is, but one can definitely show that there are denser packings than any lattice packing in that dimension. And so the question is, are there other forms of order connected to dense arrangements? And the hat is a non-convex tile, but the densest packing of hats is a tiling without gaps and overlaps. And as we shall see, that is not only not periodic, it actually has a different form of long-range order. And maybe we can have similar forms of order also in sphere packings in higher dimensions. It's completely open. Yeah. Well, maybe we skip some of the other questions. Now, what's the hat family of tilings about? So when you start to build what the local patterns are, you realize that inevitably they form a finite number of local patterns, and every hat tiling is again built from these local building blocks. And these local building blocks lead to what is called meta-tiles. These are different objects. And they admit a combinatorial inflation. That is, if you go to a larger scale, you see the same kind of building blocks, but with slightly different forms of the meta-tiles. So on each level, the shape changes a little bit. Yeah? And that hints at the existence of a certain substitutive or inflation type structure. Like for the Penrose tiling, by the way. I mean, when Penrose discovered his little drawings, he had to prove there is an infinite tiling in the first place. And if you ever try to build a Penrose tiling by just observing these rules, you will almost certainly get stuck pretty quickly. Yeah? So you build a certain finite batch, and then there are several possibilities to continue. But what you do at the lower boundary will influence what you have to do on the upper boundary unless you get stuck and can't continue. Yeah? So this kind of non-locality. And he indeed found an inflation rule, enlarge and subdivide rule, to prove that there is at least one infinite Penrose tiling. Yeah? That's important, and that is the same, very similar here. And then there are many deformations that you can make. You can rather then working with hats, you can make a little shape change that's remains locally equivalent and get turtles. And in the original paper, I invite you to have a look. There are lots of funny shapes with funny names, yeah, and they are all equivalent because they're topologically the same, and you can change from one to the other locally by some redrawing rule. Yeah, so they are all for us the same. Yeah, and now the questions are: what is the overall long-range order? So this is something that was not answered and not even addressed in the original paper of the discovery. Yeah, so the discovery and the proof, that's all fine. But the obvious next question is, so given this thing, what is the long-range order? I mean, it fills the entire plane. So if I know my head tiling here, what do I know about the head tiling in Gelsenkirchen or whatever? Yeah, is it repetitive? So is it true that finite patches reappear with bounded gaps? What would happen if I would take a head tiling and put it into an optical diffraction machine? So like the multiple slit experiment, put this thing into a laser beam and look at the screen. Will I only see sharp reflexes called Bragg reflexes, which in dynamical speak would correspond to the question, does the corresponding dynamical system under translation action has pure point spectrum? Yeah? And if I see that, is that the only contribution I see? And if that is the case, can I understand these objects as the projection of some periodic structure in some higher dimensional space? Yeah? And therefore, are they quasi-periodic? And the rest of the talk aims at saying yes, 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 and yes for these questions. Yeah? So this is the amazing thing about these monotiles. And it's the first monotile that is quasi-periodic. The other monotiles that are known are limit periodic. They are a different type of long-range order. Okay. So here are, again, the heads and the metatiles. So these colored objects are, so to say, the building blocks with 4 types of tiles that you extract from a local analysis of how you can put these things together. And every head tiling has to consist of these 4 tiles. So it's this, an unregular hexagon and a parallelogram and a cut-off parallelogram and a little triangle. So there's the triangle. Yeah, 4 tiles. That is the structure with which the authors of the original paper worked. And in essence, the proof, or one of the proofs they give, works by enumerating all possible finite configurations and proving that it's always of this form. And for that, of course, you must make sure that you don't miss one. Because if you would miss one finite patch, yeah, it could be just the patch you need to find a block that could be repeated periodically. Yeah? So that's where you really need to prove that your algorithm does not fail and does not miss a local configuration. That can be done with some logical steps. Yeah? All right. And when we looked at this, we wanted to turn this away from its lattice structure, because these heads are actually polychites, so they are built from little triangles, and therefore they live on hexagonal lattice. And analyzing these things when they are on a lattice has certain disadvantages, and to be able to replace it by something different, we need a little bit from algebraic topology called shape changes. Now, what's a shape change? A shape change is a map, F, from classes of edges to R2, and these functions, they must be closed. So if you sum over all edges of one tile, the images, it must be 0. Because if you make a shape change by, so to say, changing the edges, that better sums up to 0, because otherwise you have made an overlap or opened the tile. Yeah? And then there are some shape changes that induce mutual local derivability deformation. So what is an MLD? Transformation, that's a local rule to redraw it. And if there's a local rule to redraw it that can be locally returned, then these two things are just two ways to represent the same structure. We are not interested in those. We really want to know what shape changes can I make that really change something non-locally. Yeah? So we need the shape changes modulo this trivial degree of freedom that we redraw it locally. And there is a theorem due to Clark and Sadoun that says that the class of shape changes modulo this local redrawing freedom that we do not care about, that's equivalent to the first check cohomology of my tiling space with coefficients in R2. So that's a mouthful, that's an object. And the first reaction is, what is a tiling space, and is the check cohomology well defined? And the answer is yes, fortunately yes. And it's not only well defined, it's very nice in the sense that you can write a computer program to calculate it, which is the expertise of Franz Gehler. Yeah? So he's a gap expert and has lots of programs to actually calculate these objects. Now the tiling space, the first thing, we take any hat tiling that we have, there is at least one, we take all translates, yeah? So that's an orbit under the action of the translation group, and then we take the closure. That gives us a compact space because it's locally finite configuration, and that's the tiling space of a hat tiling. The closure and the local topology and two tilings are close if after a translation of one by at most epsilon, the two tilings agree on a ball of radius 1 over epsilon. So in larger and larger patches, they look the same. That's a so-called Feld topology, and it's the geometric analog of the product topology in a simple shift space. Yeah? So 0, 1 to the z, yeah, is typically equipped with a product topology that is inherited from the finite set. And this product topology is also of this type. Yeah? Two bi-infinite 0, 1 words are close to one another if on a long stretch around the origin they are the same. Yeah? That's the geometric analog of that. And in this topology it is compact. Okay, now these tilings that come out there can be understood as inverse limit spaces where you start with a finite patch and give, so to say, certain boundary rules, and they describe the tiling to a certain radius properly, and then, of course, deviations because you made funny identifications at the boundary. But step by step, you can make it bigger and bigger, and you get tiling spaces where, so to say, the deviation from what you actually want to describe gets sparser and sparser, and this way you get an inverse limit space. And infinite limit spaces of this type have the nice property that the cohomology theory is easy, because the cohomology theory is the direct limit of the cohomologies of these approximating spaces, which are all cell complexes. And for a cell complex, that's, so to say, the standard approach in algebraic topology. That's why you can actually calculate this stuff. Yeah? You have just this cell complex, and you calculate these groups, and actually you can do it, if you want, you can do it by hand. Yeah? So Lorenzo Sadoun did this by hand. He's an expert in that, and then came to Bielefeld and said, here, this is what I get. So, and Franz said, okay, I'll have to check that. And he ran his program and came with the same result. Yeah? So that can actually be done. Okay, now, what are the types of shape changes that are relevant here? So first of all, of course, there are linear maps. They are essential, and they also produce an essential change, but we know what they do. So for instance, I could make a shape change by just enlarging the hat. Yeah? Take just a similar copy, enlarging every edge by the same amount. Turn the hat into a bigger hat. I know exactly what's happening, yeah? So whatever is the long-range order of the original thing will give me the long-range order of the scale thing. Same, if I make a rotation, if I have a hat tiling and I rotate it, yeah, I can make a shape change that amounts to rotating everything. Again, I know exactly what's going to happen. So we are not interested in those. And then there are asymptotically negligible shape changes. So you change some of the edges, and that does change it, but if you look at the distance between changed places, and if these distances, as you go far out, converge again to the distance of the unchanged one, it's asymptotically negligible. You do something here, but it doesn't affect the relation of structures here and structures in Düsseldorf, yeah? Or epsilon in Düsseldorf and epsilon square in London, yeah? Then it's asymptotically negligible. Yeah? And then there are other shape changes. They are essential, not of this type and not of the linear type, but they do not occur for the hat tiling. Yeah? So the first theorem is that the hat tiling possesses no non-trivial asymptotically relevant shape changes. And all the asymptotically negligible shape changes, they lead to topologically conjugate dynamical systems. So when I make a shape change that's asymptotically negligible, it will not change the spectral type of the thing. It will not change the long-range order, because long-range order is about the long-range average I can do. And if on a short change it changes, but the further out it gets, it looks more and more like the original one, yeah, that will be the same. And that, as a consequence, means that, that all members of the hat family of tilings, given a certain scale, thus share the same essential topological and spectral features. So now we are in good shape. So this is quite a heavy step, and this was contributed by Lorenzo Sedun. And now we are in the situation that, knowing this, we can now look for a good representative of this class, a representative where we can do more than we can do with a hat. And that will be the cap. So we are looking for a shape change that turns this combinatorial inflation into a geometric one. Now, what's a geometric inflation? A geometric inflation is one where you blow the tiles up here by the square of the golden ratio and then subdivide into smaller copies of the original size. And you keep going. Yeah? And then the tiling will be self-similar. Yeah, so the original hat tiling does not have this property. It has a combinatorial analog of that, but this shape change with a cap tiling does. And here you can recognize, yeah, here's the hexagon. It has become a little more regular. Here's the triangle from before. Here's the parallelogram, slightly fatter. And here are the truncated parallelograms, which always come in three to form this, this windmill type, this wing, yeah? And now, this is the inflation for it. So it's not a stone inflation, but that's no problem. If you want a stone inflation, which is a term that Danza coined, you can go to a version with fractal boundaries called fractals, but you don't have to. You can work with this. So here, each blown up triangle is replaced by an hexagon of the original size. Each blown up parallelogram is replaced by this gray stuff and so on. And the additional white tiles in this picture are forced by the interior. And now you see that the additional things around it here always protrude into whatever the next tile is. So each tile knows what its neighbor is. And this is a term called forcing the border, which means that the corresponding dynamic system is minimal and all the good things. Yeah? So that's now the inflation of the cap tiling. What's the spectrum of the cap? Well, the dynamical system of the cap tiling under the translation action of R2, that's first of all, it's strictly ergodic, and its spectrum is pure point, with all eigenfunctions continuous. So it's the strongest form of long-range order. You have pure point spectrum with continuous eigenfunctions. That's almost as good as a perfect crystal. Yeah? Well, this is also true. And here's a proof. Since we have this inflation tiling, we can run an algorithm introduced by Boris Solomiak. You can check it. It's an overlap algorithm. It's a finite computation on a computer, and Franz Gehler did it, and the algorithm gave out, yes, it's perfectly fine, pure point, everything. And strict ergodicity and continuity of eigenfunctions, that follows from the inflation structure. So, case solved, proved. But what have we understood? Nothing. Yeah, because I mean, you know why this implies pure point spectrum and strong long-range order. Yeah, theoretically, because Solomiak has proved that this algorithm, when it comes out with yes, just means that, but it doesn't really tell you what's going on. Yeah, so let's look for an alternative structure, or as Rick Durrett often writes in his probability books, which I quite like. He gives a theorem and then he gives a proof, QED, and then comes a sentence, now that we have proved the theorem, let's see why it's actually true. Yeah? So that's what's coming. And to do that, we want to replace tilings by point sets, because that makes things a little easier. And therefore, I introduce a control point for these 4 tiles. So whenever I see one of these triangles, I put this orange dot here. It needn't be inside. It's just also at a very specific position. The hexagon is the blue point. This parallelogram gives the green point, and this truncated one gives this purple point. And the points are also shown in this view graph. Yeah? And now you can check that when you have a tiling, you can locally decide where the points are, what color they have, just by inspecting the configuration. And it's a little harder to see, but you can also show that when you are given the point configuration, you can inspect them and locally draw the missing edges. So whether you look at the point set or whether you look at the tiling, that's locally equivalent. That's one of these MLD rules, yeah? A local rule. You place the tiling by the point set locally. You only have to inspect. You can send a robot, yeah? He redraws it, and vice versa. Yeah? So if I understand the long-range order of this point set, I also know the long-range order of the other thing. Okay, and now comes the input from Yves Meyer from 1972 in a version formulated by Robert Moody. And this really says that if we are talking about a point set in RD that comes from some higher dimensional space, then let's set this up. So here's the higher dimensional space, and we can stay strictly Euclidean in this case, even though Meyer's theory is much more general. So the bigger space is RD times RM, and have the canonical projections to the 2 bits. And in this big space, let's consider a lattice, so a co-compact discrete subgroup, that is kind of irrationally oriented in this big space, which means that the projection to this blue space, the direct space, is 1-to-1. And let's also assume that its projection into this red space, the internal space, is dense. And because of this 1-to-1ness here, I know that every point in the projection of the lattice has a unique partner in this internal space, yeah? Because I take this point, it has this unique pre-image in the lattice, and I project it down to there, and this is just this one map called the star map. Yeah? And with this, the model set, a model set is defined as follows. We take all points in this projected lattice L such that its star image is in a certain coding region called window. That's why it's called W usually. Yeah? And think of this as saying that in this big space, I cut out a slab of this lattice with a cross section that is this window, W, and project all lattice points that are in this strip, but not the other ones. Yeah? And if you do that, you get what is called a model set, and under some nice properties that this set is compact and say the boundary as measure 0 in internal space, then it has pure point diffraction, that is what you see on the screen in this hypothetical experiment that you put the hat tiling into this diffraction machine is a point measure, so that's a countable sum of Dirac measures with a certain intensity, and this intensity is concretely given by as a Fourier transform of this window. Yeah? So this is due to Mézières. All right. And here is the intuition behind it. Yeah? So here the green thing is where we put our tiling. Here's a laser that produces a coherent beam. And then what you see on the screen is just this diffraction pattern that is described by this measure, gamma hat. Yeah? The theory for this is based on old work by Norbert Wiener about 100 years ago, who did this for finite structures, and this is, if you want, the measure theoretic extension of that. Okay, here's an example. If you would not use the Penrose tiling, but its eightfold cousin, the Amann-Benker tiling, so the two rhombi are a square and a rhombus here, yeah? Then the blue points would be such a cut and project set. And if you would put this into this optical diffraction machine, this would be the image that you see. Yeah? And the black dots are located, so that the center of the black dots is where the deltas are, and the area of the dots is the height of it. Yeah? So I have to represent it in some way. Yeah? But it really is a point-like pattern. And a picture like this is what Schechtman saw in '82 when he discovered quasicrystals just with 5-fold symmetry, or better say 10-fold symmetry. All right. Now, and for the cap tiling, this now works. You have these 4 types of points, and now you can show, okay, the intrinsic structure of these points actually intrinsically tell you we are points coming from a 4-dimensional lattice, and you can reconstruct the lattice from the positions of these points. And once you have it, you can lift the points and get the window. So sort of a reverse engineer, what would be the window to produce it, yeah? And then prove that this is correct. And that gives you this window. So it's a lattice in 4-dimensional space, not in 6, as you will read in many papers. It's not true. It's 4-dimensional space. Yeah? 6 has superfluous dimensions that causes all sorts of problems. The total window for all points is a hexagon for the control points we chose, but some of the internal boundaries are fractal-like. Yeah, this is you can get this fractal by a Koch curve type construction. So very concrete, you can do it, and you can calculate its Hausdorff dimension and everything. Yeah, so that's all under control. So that's the window. And now you have to prove. So in a certain sense, this is half of it. Now with this, you have shown that there is a cut and project set that produces possibly a superset of what we have. So we still have to show that this window does not produce something that is much more than the control points. Yeah?
Can you explain what is the role of the internal boundaries of the window? So you split the window into subsets, right?
Yes, we had. Yeah, sure. Let me just go back to the control points. So we had 4 colors, right? So we have the point positions, and if I only want to know what the positions are, I get the hexagon. But now I see, okay, I have orange, blue, green, and purple, and I want to know which points are orange, blue, green, or purple. And if I analyze that, then this window gives the answer. All the points in internal space that land in this green part will give me a green point. All the ones in this orange will give me an orange point, and so on. And all together give me all points.
And is this also part of the general scheme of the cut and project?
Yes. Yeah? In particular, this means if you would only take the green points, it would also be a cut and project set, but then only the green part of the window remains. Everything else you have to discard. Yeah? Okay. And now, because this by construction gives you a superset, you have to show that this superset is actually the set, or more precisely, that this superset has the same density as the set. Because strictly speaking, it actually is in general a superset, and that could come from boundary points. Yeah. So a projected lattice point can in principle land on the boundary of one of these fractal things, yeah, and then you would get some extra points. But as long as they are of density 0, that doesn't matter, yeah, because these measures, they don't see points that come from a window with no volume. Yeah, so you only have to show that the densities are the same, and that can be done because you can calculate in two ways. So for the cut and project set, you know the density of the lattice and you know the area of the window is just a hexagon. So from that you can calculate the number of points per unit area. And doing that gives you this funny number here. But on the other hand, we know it's an inflation structure, so you can also use Perron-Frobenius theory to calculate the frequencies of all these points. Because you have an inflation structure, and it comes with a 4x4 integer matrix, and from the Perron-Frobenius eigenvector that codes the frequencies, you can exactly calculate what the frequencies of the orange, green, blue, and purple points are, add them up, and lo and behold, it gives the same density. Yeah? And that shows that these two things are indeed up to measure 0, things that do not disturb the long-range order are the same. So we have pure point diffraction, and that by standard theory of dynamical systems means we have pure point dynamical spectrum, and because all eigenfunctions are continuous as a result of the inflation structure, it's also a known result, we have topological pure point spectrum. So we have used this measure theoretic approach, but in fact there's only one invariant measure and everything is topological. Yeah? So all eigenfunctions are continuous. All right. Now, that was for the cap, but we are interested in the hat. So we took this liberty of changing the shape. Now we want to go back to the hat. Yeah? I mean, if I would stop here, then the people interested in the geometry of the hat tiling would say, I don't understand algebraic topology, this result is irrelevant to me. Yeah? And they do say that. So we have to show what this means really for the hat tiling. Now here's an example with a one-dimensional Mickey Mouse example, the Fibonacci chain. So that's a tiling of the line by two intervals, a short and a long one, where the sequence comes from a certain Fibonacci type substitution rule. And the shape change in one dimension is just changing the average length of the tiles. And in particular, we can change the lengths of the tiles so that the blue and the red get the same length. Yeah? So here, the length is different. Yeah? So we always have to consider the length between two intersections with these regions. And now we can sort of say shear this vertical structure, and if we do that, we still get the same sequence of red and blue, but that the difference between two consecutive intersections is always the same. So what we have done here is, by a shape change, have we turned an aperiodic sequence with two types of intervals into an aperiodic sequence where everyone has the same length, but just different colors following the sequence. Still aperiodic, as long as we consider the color. Yeah? And now we have to do the same thing for the hat tiling. Well, why is this the right thing to do? So we have done this, and now if you look, what does this mean? This means when we are here, we project this point orthogonally down to the line. That's how we get it, yeah? Cut and project. And here we take the same points, but we project them in a different direction. So to go from the original Fibonacci to this shape change Fibonacci, we take the same points from the same strip, but project them rather than orthogonally to direct space, we project them in a different direction. Now we have to do the same thing for the hat tiling. And when we do that, we get this. So this is now, after this shape change, the location of these points on the hat tiling. You see, this guy is pretty rare, yeah? But we see green, blue, purple, and orange, yeah? And they all land on corners of the anti-hat. But that's fine. You can check again that this is, that sort of say the arrangement of all these points with the colors is MLD with a full tiling. If you are color blind, this would no longer be true. So the positions alone would not suffice. You need the color. Yeah? Okay. Here's the diffraction. This is the diffraction of the cap. The projector does distort it a little. Oh, that's too bad. Never mind. And this is the diffraction of the hat. So the support of these two measures is the same as it has to be when it's topological conjugate, but you might not be convinced that this is the case, right? In particular, the diffraction of the hat is actually periodic, even though the hat tiling is aperiodic. So the aperiodicity is not immediately visible. It is only visible if you analyze what's inside one fundamental domain. Yeah? And the resolution here doesn't show everything, but I have a little pseudo animation. So here is the cap, and here is the hat, and these are, so to say, steps in smaller steps, how you go from the diffraction of the cap tiling to the diffraction of the hat tiling by continuously changing the projection direction. Yeah? And here you can, maybe if you see this sequence of images, you can believe that from here to here, yeah, it's always the same positions, but the intensities change, and that is how you reach this. Yeah. All right. Now, very briefly, of course, the criticism about the hat not being a real monotile was noticed by the authors, and we were actually surprised that they didn't object to our criticism that this is not a monotile, but the reason was that they were already working on a real monotile. And that's the spectre. So the spectre is really this object, and it was derived from the hat and the turtle tiling in a certain combination. This is not a lattice polygon anymore. And it again has the property that it tiles the plane, but only aperiodically, provided you do not allow the reflected version. But that can easily be done by changing the outer shape. Yeah? So if you deform, this is also a shape change, yeah? A local redrawing. But if you go from here to here, it is clear that if you take the reflected guide, it will never fit. So if you take this, then it is true that it tiles the plane only aperiodically like the hat, but this time it's a single tile and not its reflected version. So what's the drawback of this example? The drawback of this example is that this guy in every spectre tiling occurs in 12 different orientations, but it has only 6-fold symmetry. So there is in fact a spectre and its rotated versions by multiple of 60 degrees, and a shadow spectre, 30 degrees rotated, and then multiple of 60 degrees, and they occur with different frequencies. And therefore, even if you prescribe an orientation for the spectre, as you always do, so this is the spectre, there are two types of tilings. One where the majority points this way, and one where the majority points 30 degrees. So two ground states. Yeah? Okay, otherwise, it's the same old story, just technically more complicated. So let me just show you some pictures. Again, you get metatiles, and again, the cohomology group is the smallest possible, so there are no relevant asymptotically non-negligible shape changes. So we can look for a self-similar member in this class, which is now the Casper tiling. Casper the friendly ghost, yeah. And all these names are, of course, due to Lorenzo Sadun. I mean, you have to be a native speaker to come up with these little things. And well, by the way, why is cap tiling a good name? Of course, it's a cap, but it also stands for cut and project. Yeah? So it's really a good name for it. And the same is here. So Caspar is cut and symmetrically project. Okay. Same old story. You have these meta tiles, you have an inflation. This is a patch of this other tiling with the self-similar tiling. It looks less beautiful maybe, but it's a perfectly fine tiling, and certain of these tiles always come in groups, so we can introduce control points by giving single control points to these and then single control points to these two pairs, because they always occur in this group, and one control point for this triple, and that makes 5 type of points, and the corresponding window is this. Now everything is fractal, yeah? So in the previous one we had this hexagon and then fractally split, and here everything is a fractal. And these are rosy fractals, yeah? So these objects here that are here, they are the unique solution to a contractive iterated function system in R2. Yeah? And that's also how you can calculate it. And here are the diffraction of the spectra and the Caspar. They look much more similar than in the previous example, because the Caspar is not a lattice tiling. It is itself not bound to lattice structure, so you have to look more carefully to see the difference, but you can, yeah? So for instance, here you can see it's really different, yeah? But they are very close by. All right, so that brings me to my conclusion or outlook. So we can calculate the eigenfunctions from here, which are the Fourier transforms of these funny rosy fractals. Now, try to calculate the Fourier transform of the characteristic function of a set with fractal boundary. You can't do that by standard methods. So you need theory of cocycles. Yeah? But one can do it. So there's a lot one can do about these rosy fractals. They do produce interesting Markov partitions, and even though we have said that multiple times in previous papers and also in the papers on this, there are now lots of papers appearing making a big fuss about the Markov partitions that are here. But the Markov partitions are trivial once you have the window. It's just a direct product of the tile with its window. That gives a partition of the, in this case, 4-dimensional torus into partially fractal sets, and they are the Markov partitions of the dynamical system. Surely one would be interested, now that we have some of these monotiles, to understand better where do they occur. Are there more? Well, Kaplan and Myers have cranked up their computer search, and they have now investigated millions and millions of candidates of polychites and other lattice polygons, and they have not found a single other example beyond the hat. And that was a bit surprising to me. I don't have any good understanding of why this is so rare. So there's definitely something we haven't understood. Now, the real challenge, of course, will be to find a monotile in 3 space, because that would be ultimately relevant for understanding some of quasi-crystal structure. Yeah? So in 3-dimensional space, there are these quasi-crystals. They are there. And if you find a single building block that would force aperiodicity with quasi-periodic long-range order, that would be a good candidate. Yeah? So that's, but so far, no progress, and the computer searches in 3 space are so much more expensive in terms of computer time that at the moment no one has achieved that. Yeah? The role of almost periodicity is unclear. I mean, in a certain sense, these monotiles are an accident. Why? Both are related to quadratic irrationalities. First one to the golden ratio, the second one to 4 plus root 15. It's also quadratic irrational. Now, the quadratic irrational can only occur as an eigenvalue of an integer matrix if the matrix has at least dimension 2, which means there are 2 prototiles. You can't avoid that. And that means what we see is a shape change that, in a certain sense, by accident gets congruent. Yeah? While for the limit periodic one, where the inflation factor is 2, there's no such obstruction. So this is not understood what that means. Yeah? So there are lots of interesting open questions. And definitely is this a case where we can ask ourselves, how well do we actually understand Euclidean space? I mean, in recent years, a number of conjectures about geometry in Euclidean space have been disproved because our intuition is based on 1, 2, 3, and perhaps 4. But how it looks in 7-dimensional space or in 10 to the 10 to the 63-dimensional space, we have very little understanding. And therefore, I think this really is an important discovery, and it's only the beginning. Yeah? And I expect quite a number of interesting results coming in the near future. Thanks for your attention. Here are some references.